Okay, welcome back, everybody. Yesterday, in the last lecture, we defined and discussed the idea of a matching. So a matching is a set of independent edges. Independent meaning, of course, a set of edges where no pair of a set of edges where no pair of the edges share a vertex. We defined what it meant to be M saturated. M is a matching of some graph, being M saturated. Is to belong to one of the edges in this edge set M. So if M is a matching, any of the vertices belonging to any of the edges in M are said to be saturated by M or said to be M saturated. And then any vertices not belonging to that matching are said to be M unsaturated. And then if a matching saturates every vertex of the graph, it's said to be a perfect matching. A maximum matching is a matching that has the largest possible cardinality. A maximal matching is a matching that cannot be enlarged by including another edge. As we saw, there are examples of matchings that can be maximal but not maximum. So the example that we saw specifically of these things yesterday. Does G sub 1 have perfect matching? The answer was yes, and here it is. I just exhibited it. So this matching, it is an actual matching, right? All those edges are independent, and this includes, saturates every vertex of G1. G2, here was an example of a maximum matching. It contained 4 edges, and you can argue for this graph that 4 is the largest possible number of edges that could be included. In this second matching, M sub 2, is a maximal matching in the sense that this cannot be, I can't include a single other edge here in the graph and still have this be a matching. So this is as large as this matching can be, given these 3 choices here. But it's not maximum, clearly, because there's a matching that has a greater cardinality, right? So, all right. So these are pretty basic examples to illustrate these notions. This is important because going forward, the theorems that we're going to talk about mostly today are going to reference matching a lot. So if you're confused about what exactly is being talked about, go back to these examples, these definitions, to help yourself. So next, I wanted to discuss Hall's theorem and SDRs. We're going to see what an SDR is here in a second. But before we do that, as always, we got to define a bunch of stuff. So in this case, given a graph G and a matching M of G, or of some vertices in G. Maybe I'll just say a matching. It's understood if I have a matching of G, it's a collection of some number of the edges of G. Okay, so given a graph G and matching M and M, alternating path is a path in G where the edges of the path alternate between being edges in M and edges not in M. Okay, so it is a path in G whose edges alternate between being edges in M, these might be called M edges, and edges not in M, or non-M edges. Very aptly named. Okay. A related concept is that of an M augmenting path. An M augmenting path is an M alternating path where both end vertices are M unsaturated. Where both end vertices are M unsaturated, i.e. they're not in M, right? You might say, what do you mean they're not in M? M is a collection of edges. When I say that a vertex is not in M, it's an informal way of saying it's M unsaturated. I mean that it's not contained by an edge in M. So if I was being a little bit more precise, maybe I would say, instead of this, I would say not contained by an edge of M. Or not incident with an edge of M. Okay. All right, to understand why we call this M augmenting, we'll take a couple of results here before we realize like why we're using this sort of language. Let's do an example to see what it is that's going on here. So let's give myself some more room. So let's do a quick example. I'll label these right so that these canned examples match. No pun intended. So let's see here. Make this vertex bigger. Same here. Okay. So we'll call this vertex B, this one C, this one A, this one D, this one E, then G, F, H, I, and then call this one J. Let me pick an M matching. So let M be, we'll say, let it be the edges AC. We'll let it be contain the edge DE. GF. And HI. Okay. All right. So here's our matching M. Of course, it's obviously a matching because these are obviously independent edges here. So this is definitely a matching. What is an example of an M alternating path? Let's consider the path. Let's consider the path that begins at C. So C, A, D, E, I. So it starts at C. It's from C to A. So that is an edge in the matching M. The next edge goes from A to D. That is an edge not in the matching M. The next edge is from D to E. That is an edge in M. The next edge is from E to I, which is an edge not in M. So we have a path from C to I. It goes like this: C to A to D, D to E, E to I. Okay. But this first edge is in M, not in M, in M, not in M. So this is an M alternating path. So this example is an M alternating path. Now, quickly, if I ask you, is this M augmenting, according to our definition? Let me bring our definition back for a second. An M augmenting path is an M alternating path where both of the end vertices are M unsaturated. Well, here, one in vertex C, the other is I. Both of those are vertices in an edge of M. So both of those are actually M saturated. So the answer is no, this is not an M augmenting path. Consider the path J, G, F, A, C, B. So begin at J, go to G. That's not a path in M. Or sorry, that's not an edge in M. Okay. So this is not an edge in M. Okay, so not an M. From G to F, now that edge is in M. From F to A, that edge is not in M. From A to C, that edge is in M. From C to B, that edge is not in M. And the thing you notice here is the endpoints of this. So this is definitely an alternating path, right? Not an M, in M, not an M, in M, not an M. Okay. And what you notice here about this path is that both endpoints are M unsaturated. J is not incident with an edge that's in M, neither is B. No, this is an M augmenting path. Okay. Now, before you have even had a chance to ask a question about these things, let's see maybe let's see how this new notion is related to what we've discussed previously. So, following theorem, this is Burge's theorem. Which says that if we let M be a matching in a graph G, M is maximum. Recall that means it is as large as possible. It contains as many edges as it possibly can. The largest number of edges for a matching in a graph. So let M be a matching in graph G. M is maximum if and only if G contains no M augmenting paths. Okay. So, what's the proof of this? Let's do the forward direction, and I'll leave the reverse direction for you to read over. So, what is the forward direction here? So, assume M is maximum. That is, it contains the most edges, right, that it can. Okay, suppose that P, which I'll say is a path indicated by vertices v1, v2, and so on to vk, is an M augmenting path. What is the idea here? The idea is to use proof by contradiction, and the reason for this is because I just feel like I need to assume I need to assume that I do have an M augmenting path to give me something to get my hands on. Showing that there can't possibly be an M augmenting path, how would I do that? Unless I had some other results about M augmenting paths and their existence, it seems hard to relate it to anything immediately. So to get my hands on something, I suppose that I do have one, and then hopefully see why that can't exist. Okay, so that's just the idea here. Since an M augmenting path is alternating, right, this actually puts a restriction on how many vertices can be in this path. Right? Since P is necessarily, since it's M augmenting, every M augmenting path is necessarily M alternating. Since it's M augmenting, the endpoints must not be in M, right? They must not belong to an edge in M. They must not be an endpoint of an edge that belongs to M. So V1 and Vk we know are M unsaturated because this is an M augmenting path. Since the path also has to be alternating, K has to be even. And I know more. I know the edges that are in M. So, for instance, V1, V2, that edge can't be in M because V1 and Vk, because this is an M augmenting path, are M unsaturated. So V1 to V2, that edge, and V sub k minus 1 to Vk, that edge is definitely not in M, and none of the alternating ones are in M. But every other one is in M, right? So, and I also know that the edges V2 to V3, V3 to V4 would be not in M because this is alternating. So V4 to V5 would be the next edge in M, and so on, up to the last one would be V sub k minus 2, V sub k minus 1. That is the last edge before the final edge, V sub k minus 1 to Vk, which we know has to not be in M, because this is an M augmenting path, so Vk is M unsaturated. These edges are edges of M. Right. Similarly, I mean, for literally the exact same reason, the edges V1, V2, V3, V4, and so on, all the way to V sub k minus 1 Vk, are edges not in M. This is just the definition of being an M augmenting path. Okay. Now, how does this help us? What does this allow us to do? Of course, I could draw this picture, right? This is for drawing the path, right? this is V1, this is V2, V3, V4, V5, and so on out to these last two. So here's Vk, here's V sub k minus 1, here's V sub k minus 2. Obviously, this alternating works like here's the first edge that's in M. This first one can't be because it's M augmenting. This one can't be because it's alternating. So then this one is the next edge in M. This one is the next edge in M. Here is the last edge in M that shows up. This one's not. So this is what it looks like, right? This is what we're keeping track of in our heads when we're thinking of an alternating path or an M augmenting path here. Okay. Let's define another matching. So define M sub 1 to be the set of edges that looks like this. We will take M we will get rid of the edges V2 to V3 and so on all the way to V sub k minus 2, V sub k minus 1. So all the edges that we got here, we'll get rid of those. And then we are going to union those with the edges we know are not in M, which are the edges V1, V2, V3, V4, and so on up to V sub k minus 1, V sub k. Now, let's think for a second here. All right, so first of all, I took, maybe I'll put both of these on at the same time. Here, I took M. I know that these are not necessarily all of the edges in M. This is just some M alternating path. It's not guaranteed to contain every single edge of M or anything, but whatever edges of M it does contain, I take M, I get rid of those, and then I add in the edges that I know are not in M. And in this way, what I have left is guaranteed to be a matching. But here's the thing. It's a matching. And what do you notice about how many edges this has in it? Right? How many edges does this have in it? So if you're careful, you can notice that this is a matching and has one more edge than the matching M that we started with. Think about how the fact this was an M augmenting path, the fact that such a path has k vertices in it where k has to be even, it's forced to be even here, and think of why that means taking out these edges and throwing these in is going to get you one more edge. Why is that a problem? Well, we assumed that M is a maximum matching. We assumed M was maximum. And this is a contradiction. Thus, what was the only thing that we assumed in this process that was an issue? It was this assumption. Suppose that this was an M augmenting path. Such a path can't exist. Thus, there cannot exist such a path P, which is exactly what I wanted to show in this direction. That if M was a maximal matching, then G could not contain an M augmenting path. The backwards direction, you can investigate this yourself. So the backward direction you can see on page 105 of the textbook. I just wanted to do the forward half. Okay. So that's interesting. That's a nice characterization of what's going on here as a way to describe whether a matching is maximum or not, and what that means about the graph G containing certain alternating paths, alternating with edges in M. So before I state the next named theorem, I've got to do the thing that I've always done in this course, which is do a bunch of definitions, talk about some terminology and notation before moving on to this this next very nice named theorem. So let G be a bipartite graph with partite sets X and Y. We say X can be matched into Y if there exists a matching in G that saturates the vertices of X. So if there exists a matching that saturates the vertices of X, which means that there exists a matching that contains all of the vertices of X as endpoints of some of the edges, if every single one of them is contained as an endpoint of some edge in a matching, then we say that X can be matched into Y. Okay, so let's do like an example here. So let's say we have bipartite graph that looks like this. So let me draw in some edges here. Let's see here. There we go. Okay, so it's obvious what the partite sets are here. Question is, if this is my X and this is my Y, can X be matched into Y? That would mean that there exists a matching in this graph that saturates the vertices of X. I just need to find one of them. So what if I include this edge and this edge and this edge? So those three edges saturate the vertices of X, and they are a match, or they are a matching in this graph. right? But you notice when I was filling this out that, for instance, if let's say that the only connection here, right, the only edge between this vertex and any of the vertices here was this one. So this edge didn't exist. Maybe this vertex was connected here. Would I be able to say that x could be matched into y? Well, no, because the only possible edge to include here would be this one, and in the way that I'd selected these first two edges, I would have a problem here because now these two edges wouldn't be independent. Now, could I have still found a, a matching of x into y? Well, you have to think about that altered graph for a second, right? But it is possible that no such matching exists. So here's an example. Let's say I have the bipartite graph that looks like this, which does basically the thing that I described over here. Okay, so here's my partite set x, here's my partite set y. The answer is, can x be matched into y? So here the answer was yes. Can x be matched into y here? Well, no. So the way to think about this is for these two graphs, or sorry, for these two for these two vertices, the only possible edges to include are this one and this one. And those two edges can't be included, obviously, because they share an endpoint, so those are not independent edges. So there is no possible matching of x into y. Okay. Then the question seems natural. What conditions on a bipartite graph must exist if we want to match one partite set into the other? That's a natural question to ask. The answer to this question is provided by Hall's theorem, which we'll see on the next page. Okay, so what is Hall's theorem? Let G be a bipartite graph with partite sets x and y. X can be matched into y if and only if the cardinality of the neighborhood of a set S is greater than or equal to the cardinality of the set S itself for all subsets S of the vertex, the partite set X, sorry. Quick reminder, what is the neighborhood? How did we define the neighborhood of a subset of vertices? So the neighborhood of a subset of vertices was defined to be the union of all of the open neighborhoods of single vertices in that vertex subset. Okay. So that was what the neighborhood of a subset of vertices was defined as, rather than the neighborhood or open neighborhood of a single vertex. It's a union of a bunch of those neighborhoods of single vertices. Okay. So we can prove this one. Let's do the forward direction. This will be pretty quick. Suppose x can be matched into y. Let S be some subset of x. But then S itself can be matched into y. By the same matching. And thus, immediately, we see that this cardinality of the subset S is less than or equal to the cardinality of the neighborhood of S. Why? We should look at a picture here. So the idea, we have a partite set. So whatever it is, here's my x, here's my y. Right? We assume x can be matched into y. So there's a matching here that saturates the vertices of x. Because it saturates the vertices of x, any subset of the vertices of x, you can just use the same matching for those particular vertices. So say that S is your subset of vertices. So here's S. It contains some number of vertices, right? Here they are. Okay. Use the same matching that matched X into Y to match these vertices over here. To vertices. Now, because of how partite sets work, right, what you get over here, whatever these vertices are, they are a subset of the neighbors, right, the open neighborhood of S. Why? Well, remember what this is. Like I said, this is the union of all of those singleton open neighborhoods of a single vertex. The open neighborhood of a single vertex is all of its neighbors, right? Not containing the vertex itself. That's why it's the open neighborhood. So it's the neighbors. But of course, these are the neighbors of these vertices, because this is a bipartite graph, and we have this matching. So these are necessarily a subset of N of S. Because of we have this matching, we know that the size of S has to be less than or equal to. It might be equal to, it might be exactly equal to, right? If this matching produces vertices here that are exactly all of the neighbors, then this would be equal to, but it can't be greater than, certainly. So this estimate has to exist in this way. But that is exactly what we wanted to show, right? That is the forward direction. So we're done with the forward direction from that picture. What about the backward direction? So the backward direction is, suppose that the size of the open neighborhood of S is greater than or equal to the size of S for all subsets S of X. Okay. So the thing here is, what do I want to show? I want to show that X can be matched into Y, right? So want to show X can be matched into Y. Well, how do I do that? The idea is I want to use Burger's, or not Burger's, Burgess theorem. But what did Burgess theorem even say, right? I need to go back. See, Burgess theorem said if M is a matching in a graph, it is maximum if and only if the graph contains no M augmenting paths. It's not entirely clear how this is going to help me, maybe, until we draw some pictures. But let's just say I'm divinely inspired, right, to want to use Burgess theorem. In order to do that, let's suppose that a matching exists and is a maximum matching. So let M be a maximum matching in G. I'm not saying that this M is a matching of X into Y. That would be begging the question, right? That would be circular reasoning here. So I'm not assuming that. I'm assuming it's just a maximum matching. Okay? So let M be a maximum matching in G, and suppose that some vertex U in X is not saturated by M. Now, if such a U does not exist, here's a good thing, because the question you might have asked in your head when you heard me saying let U be a vertex in X that's not saturated by M, you could have simply had the question, how do you know such a U exists? Maybe it doesn't, right? Maybe there is no such a U, because we're doing this completely generically, right? So not allowed to pick something special here. What if such a U doesn't exist? Well, if such a U does not exist, then every vertex of X is saturated by M. And thus, M is the desired matching, right? And we're done. Right, because we're looking for a matching that saturates all the vertices of X. A matching that contains every vertex of X is one of the endpoints of one of its edges. Okay. Every time I rephrase this, you should understand why we come up with all these words, right? You might be complaining and saying, oh, M augmented, M saturated, M alternating. Like, why are there so many different words for this? When it's like, you feel like you should just be able to say vertex is not an M, but that's confusing because M is an edge set, so it only contains edges. But then you have to say, well, okay, the vertex is not an endpoint of an edge contained in M, but because you have to be okay letting it be either endpoint, you can't say which endpoint it is, right? And I know that doesn't matter for us, but there's a lot of things going on here where, unfortunately, to be precise in fewer words, we have to introduce a bunch of extra terms. Okay, So yeah, if such a U does not exist, then this matching is the desired matching since every single vertex of X is saturated by M. So there has to exist one that's not, or I mean, there doesn't have to, but if there doesn't exist, we're happy that this is the case because this means we're done. So suppose that U is not saturated by M. What does this picture look like, right? I have my partite set X, my partite set Y. I have some matching that is like this, but then there is some vertex U that is not contained in this matching. So here's some of the, let's say we've done all of the matching in this graph, but U isn't saturated by this matching, so there it is. It's not in an edge for this matching indicated. Okay, define A to be the set of vertices in G that can be joined to U by an M alternating path. Now, this is, you might think of this as being kind of a complicated set here, but don't think too hard yet about like what this set is specifically. We're not necessarily interested in trying to compute exactly the vertices that belong to this set. We're more using this set to guarantee this property. You'll see what I mean here in a second. All right. So let S be the set A intersected with X, and let T be the set A intersected with Y. So let's think for a second. S is the set of all vertices in X that can be joined to U by an M alternating path. And T is the set of all vertices in Y that can be joined to U by an M alternating path. That's what we're doing when we intersect these. So we are using the set A to have this property, and then we are basically using it to just conveniently write these sets as the set of all vertices in X that have this property, the set of all vertices in Y that have this property. Okay. Now, what does Burgess' theorem say? Well, again, to remind ourselves what Burgess' theorem, actually the statement of Burgess' theorem. If M is a matching in a graph, its maximum if and only if it contains no M augmenting paths. So if it's maximum, the graph can contain no M augmenting paths. We assumed that the M that we're dealing with is a maximum matching, right? So G cannot contain any M augmenting paths. Okay. Well, if U is not saturated by M, right, then if a path begins at U, right, and is M alternating and ends somewhere not in M, that would be an M augmenting path, right, which shouldn't be able to exist. So, what does Burgess' theorem say? One, it says that every vertex of T is saturated by M. Why? The short version, which there's just track through all of this setup, right? If a vertex in T was M unsaturated, then G would contain an M augmenting path which is impossible since M is maximum. By Burgess' theorem. Because T is the set of all vertices in Y that can be connected to U by an M alternating path. And U is not saturated by M. So U is a valid starting point for an M augmenting path. And if it ends at a vertex in Y, right, that is M unsaturated, that would be an M augmenting path, but that violates M being maximum by Burgess' theorem. So every vertex in T is M saturated. That's the first thing. Similarly, the only unsaturated vertex of S is U. Why? If there was another one, if it was also M unsaturated and not equal to U, then I could form an M augmented path from U to V, which violates M being maximum by Burgess' theorem. Okay. Maybe you see now why we're using the word augmenting or M augmenting for this. When we see the relationship between this and the matching being of maximum size, right? Okay. So once you have Burgess' theorem, you see that an M augmenting path would give you a way of including an extra edge at least. So it is M augmenting in the sense that if you have a matching and an M augmenting path in the graph, then that matching can't be maximum. And that M augmenting path describes to you how you could throw in an extra edge, at least one extra edge, right? That's the idea. Okay. So these are the two facts that I get from Burgess' theorem. Okay, once we've unpacked what Burgess' theorem tells us. Okay, so every vertex of T is M saturated, and every vertex of S minus U is unsaturated, right? So maybe I'll restate this. So every vertex of T is M saturated, and every vertex in S minus U, so this is all the vertices in S except for U, is also M saturated. Right? U is the only one that's M unsaturated here. Okay, but what does this mean? But this means that the size of T, remember T is all of the vertices in Y that can be joined to U by an M alternating path. Okay, so then the cardinality of T is actually the cardinality of S minus 1. But then, again, by Burgess' theorem, and the definition of T, the neighborhood of S is simply T. But in that case, the cardinality of the neighborhood is the same as the cardinality of T since they're the same set, which is the cardinality of S minus 1, which of course is strictly less than the cardinality of S. This is what we wanted here. But this is a problem. Why is this a problem? Because at the very beginning of this case, we supposed that the size of the neighborhood of S is greater than or equal to S for all subsets S. We defined a subset S on the previous page. Doesn't matter how we defined it. I was told that any subset of X should satisfy this. So I suppose this was true for all subsets of X, and we found out that actually it's not. We get a contradiction here. So, what was the thing that led to this contradiction? Going all the way back, we suppose there was a maximum matching. That's fine. There's nothing wrong with assuming that. So then what is the first thing we assumed that we never justified? We just assumed it, and then it is the thing that led us to this place. Oh, the assumption that we had a vertex in X that was not saturated by M. That's the first assumption we made that was not justified. We just assumed that this thing existed. This is the thing that can't exist, right? So thus, such a U in X that is M unsaturated cannot exist, i.e., every vertex of X is M saturated. Thus, M is the desired matching of X into Y. And that is it. We have proved Hall's theorem. So you might say, wait, didn't we justify the existence of this by saying if such a U does not exist, then every vertex is saturated by M and we're done? Yes, we did, and that's why we didn't consider the other case. So consider the case that this isn't saturated by M. We got a contradiction eventually. So yeah, it turns out that such a thing just didn't exist in the first place. So we were in the case we wanted to be in where we were done and we just didn't know it. We had to find a contradiction first to say, ah, yes, all right, we can't assume that such a thing exists. This is Hall's theorem. Okay. Now for something a little different. Remember this application I talked about at the beginning of all of this matching stuff where I talked about Senate committees and selecting an executive council for some Senate committee. Now let's kind of bring into play what it is we're even talking about with that stuff. So there's definition. This is a definition of what are called SDRs, or system of distinct representatives. This is the notion of an SDR for short. So what is this? Given some family of sets X. You might object that I'm using the word family here. What's a family of sets? Is it different than a collection of sets? Is it different from a set of sets? No. But there is a reason. You might be skeptical to talk about sets of sets. You know anything about Russell's paradox and like foundational logic. The way we use kind of like naive set builder notation, you got to be a little bit careful with it. So there's some things that can go wrong. So when you talk about sets of sets, because everything we're talking about is finite and stuff like that, we're talking about finite collections of sets in all these cases, it's not a problem. But you know, anytime you say a set of sets or a set of all sets that have some property, that then you start getting into all kinds of issues. And so that's why linguistically you'll see people coming up with all sorts of euphemisms and swaps that you can make instead of saying a set of sets or collection of sets, or so you'll say collection of sets, family of sets, whatever. Yeah, so given some family of sets X, so this is a set of sets, a system of distinct representatives, or SDRs, for the sets in X is a representative collection of distinct elements from the sets of X. So let's do an example. Let's let S1 be the set that contains the elements 2 and 8. Let S2 be the set that contains the element 8. Let S3 be the set that contains the elements 5 and 7. Let S4 be the set that contains the elements 2, 4, and 8. Let S5 be the set that contains the elements 2 and 4. Okay. So, if I let x1 be the set of all of these sets, or let's not do all of them, let's do the first 4. So it's the set of the 4 sets S1, S2, S3, and S4. Then this does have an SDR. What is its SDR? So S1, 2, 3, and 4. We'll pick 2 as the representative for S1. 8 is the representative for S2. It's the only choice. For 3 and 4, so I've already chosen 2 and 8 here, so I want to choose 4 for S4. 4 doesn't show up here, so it's not even a factor, so I can choose whatever I want. So maybe I choose 7. And then here I pick 4. Is an SDR for X1. But if I let X2 be the family S1, S2, S4, S5, then X2 does not have an SDR. Okay. So why not? Well, let's try. So S1 and S2. Clearly, since I want both of the, in S2 I only have the choice of 8. So 8 has to be the representative for S2. If 8's the representative for S2, I got to pick 2 for S1. So 2 and 8, all right. For S4, I can't pick 2 or 8, so I have to pick 4. For S5, I only have 2 or 4 as an option. Either of those I pick, if I pick 4 here, I won't be able to pick it in S4, and I won't be able to pick 2 and 8 because I already chose them for S1 and S2. S1 and S2 kind of nail down that 2 and 8 have to get chosen here, so that removes 2 and 8 here, so I have to choose 4 here, but now I can't choose 2 and 4. So this does not have an SDR. And you see this example like fully illuminates what is involved in this process. Okay, but question, very natural of course, right? Under what conditions will a finite family of sets have an SDR? And the answer is the following theorem. So let's see what that theorem is. The theorem, let S1, S2, and so on up to some Sk be a collection of finite non-empty sets this collection has an SDR if and only if for every t in set of indices 1 to k, the union of any t of these sets contains at least t elements. before we set about proving this, let's first go back and see why it succeeds for x1, or maybe even just why it fails for x2. All right, so let's see here. So for x2, we would need the union of any one of these to have at least one element. Okay. The union of any two has at least two elements. That is actually true. The union of any three has three elements. That is also true. Even if you pick S1, S2, and S5, you get it. If you pick S4, S5, S4, and S2, you still get it. You get it with all of these. But the question is, does the union of every four of these, that's all four of them, contain four elements? And the answer is no. So notice that the union of here, S1, union S2, union S4, union S5, how many elements does that have? Actually, it only has three. It's 2, 4, 8. Only three elements. But there's four of these in the union. So it fails. Notice that the union of the four sets here, S1, S2, S3, S4, is going to have five elements, right? 2, 4, 5, 7, 8. So the union of those four have five, so that satisfies it because it has at least four elements, and this satisfies it for every other size here. One, yeah, all of them have at least one. All of them have at least any union of two has at least two. Any union of three has at least three, and any union of four has at least four. So that's it. This satisfies this theorem. Okay, since each S sub I is finite, the finite union S, which is just the union of the S sub i's, is also finite. And say that its elements are denoted A1 to AN. So we've just counted the elements up to N. Now, the idea is we construct a bipartite graph between X, which is the collection of those sets S1 to SK, and Y, which is the elements of the union of all those things that I've labeled A1 to AN. We place an edge between some SI and some A sub j if and only if this A sub j actually belongs to that S sub I. Right? Some of them are going to belong to some of the sets. Right? That's how we got them. Right? They are elements in this union. So just by definition, any element in this union belongs to one of those things. Right? It belongs to one of the S sub i's. Okay. But then what does Hall's theorem say? What does this picture look like? Here I have X, and the vertices in X are the sets, right? They are labeled by the sets up to S sub k, and the vertices of our set Y are the elements in the union. Okay, and we connect this bipartite graph with edges in this fashion. So then Hall's theorem, this is definitely going to be a bipartite graph. So Hall's theorem now says what? It says that x can be matched into y if and only if the cardinality of A is less than or equal to the cardinality of the open neighborhood of A for all subsets A of X. But then the collection of sets has an SDR if and only if for every T, the union of any T of these sets contains at least T elements. That's what this inequality says, right? Thus, the collection of sets if and only if for every T between 1 and K, the union of any T of these sets contains at least T elements. So unpack why this statement is exactly what I just wrote out here, together with Hall's theorem. I mean, this is the conclusion of Hall's theorem, but this is, why does this mean that? Okay. Sometimes this Hall's theorem is referred to as Hall's marriage theorem. So that's it's very obvious where and how, to what extent the combinatorics is creeping in here, right? Like we haven't been enumerating quite so much. We've done a little bit of it, but it's obvious now how much more the combinatorics is creeping in. We're going to keep seeing that until we swap over to combinatorics. So the remaining stuff that we're doing in graph theory has a heavy combinatorial bent when it comes to this, and when it comes to kind of its viewpoint. So I have to provide some definitions first before I can state the next theorem with big name that I want to state. So here's some definitions. A set C of vertices in a graph G is said to cover the edges of G if every edge of G is incident with at least one vertex of C. Okay, this is a very intuitive definition. Such a set C is called an edge cover of G. Okay. So, let's do some examples. So here, I'll call this graph G1. Okay, let's label it. This is A, B, C, D, E, F. Okay, so G1 has edge cover B, D, E, A. Right? Can you find a smaller one? So you pause the video for a second and try to see if you can find a smaller one that contains less vertices. Actually, A, E, and F are all we need. All right, so A, E, and F will work. So another edge cover of G1 is just simply the vertices A, E, and F. Okay. Now, can we make it even smaller? Can we do it with two vertices? The answer for this particular graph is no. But of course, that brings up interesting question of like, what's the smallest edge cover, right? What's the smallest size of an edge cover of some graph? Okay. We could say in this way that this is a minimum edge cover of G1. Okay. Let's do another quick example. Mm, let's connect these two and then these two. We'll call this V1, V2, V3, V4, V5, V6. Call this U1, U2, U3, U4. Call this graph G2. Okay, this is a bipartite graph. So this is a nice other example to consider. So V1, V2, V3, V4, V5, and V6 is an edge cover of G2. So is say U2, U6, and U1, or yeah, U2, V6, and U1. Yeah, we'll do it. Sorry, not U6, V6. Okay. Is another edge cover of G2. Question is, can you find a smaller one here? Possible to find a smaller one, or is this as small as it gets? So, this is a build up to the following. This is a theorem due to Koenig and Egervary. Probably need to look up how the second name is pronounced. I at least know how Koenig is pronounced. This is the Koenig-Egervary theorem, which says let G be a bipartite graph. The maximum number of edges in a matching in G is equal to the minimum number of vertices in an edge cover of G. Okay. I am going to stop here because I'm out of time. But this theorem, we're not going to, well, maybe I'll prove it. It's not too long. So yeah, I'll probably prove this next time. Proof next time. I'm also going to mention that this is our first instance of a theorem that relates the maximum number of one thing to the minimum number of another thing. There are several such results in graph theory specifically about that do this sort of thing. I'm going to give a few more of those examples tomorrow in the first maybe 10-20 minutes lecture. After that, we'll do some Ramsey theory tomorrow. Finish up any remaining Ramsey theory bits that I wanted to do on Monday, and then we're on to combinatorics. We're leaving graph theory behind. So tomorrow's lecture and maybe like 10 to 20 minutes of the lecture after that will be the last graph theory lectures in the course that are specifically just focused on graph theory. Like I said, we may return to infinite graphs and things later if time permits, but we're moving on to combinatorics after this little bit. So anyway, so if you were primarily interested in the course for the combinatorial aspect, then you're about to be happier. If you were primarily interested in it for the graph theory aspect, don't worry. It's like all these things are very related. There's a reason why they are stuck together in this way, and there's a reason why it's chapter 2 of the textbook. So anyway, we're continuing on. Your midterm, your first exam will be same format as the homework, basically. And I will post it Friday afternoon, and it will be due Monday at 11:59. So you'll have a few days to work on it. It will concern all of the graph theory stuff. So basically, anything in Chapter 1 is fair game. Like I said, you'll post it. I'll let you know when you have access to it. Same format as the homework, so it's not during any particular time window or anything like that. You're going to have a few days to work on it. So anyway, that is that. I will see you all for lecture tomorrow.